The Great Pyramid of King Khufu, this is just one of the Great Pyramids, was built of limestone in Egypt over a 20-year time period from 2580 BC to 2560 BC. Its base is a square with side length 756 feet, and its height when built was 481 feet. It was the tallest man-made structure in the world for more than 3,800 years. The density of the limestone is about 150 pounds per cubic foot. A, estimate the total work done in building the pyramid. And then B, if each laborer worked 10 hours a day for 20 years, for 340 days a year, and did 200 foot-pounds per hour of work in lifting the limestone blocks into place, about how many laborers were needed to construct the pyramid. All right, so the point of this problem is it's just illustrating the concept of using integration to calculate a parameter. And this section was, they used, the example parameter that they used was work from physics. But as I've mentioned in the previous videos, don't get bogged down. Don't be so focused on understanding the physics here, like the concept of work. This is really just about the concept of integration. Integration being applied to like a real life scenario. And so, this is a simplified case here where what they're really asking is, it's not the work required to build the pyramid, because, we're not, what we're going to see is, it would take work to lay the first base of limestone. And we're not going to consider that. And why not? Because they didn't lift it. They didn't have to technically lift any stones up to put those stones in place, but they actually did, right? They had to pick them up to move them. But we're just going to be looking at, this is a very simplified case, and it is just because, this isn't a physics class. It's a simplified case just to practice the integration process. It's all about the work required strictly to lift these stones up, to put this second layer of stones, third, fourth, all the way to the top, to lift those stones against gravity. That work, the total work to build the pyramid in lifting this second layer, third layer, fourth layer, all of those stones against gravity. I mean, actually, no, I take it back. The way we're going to do the integration, we're actually going to kind of be calculating the first layer too. I mean, I'll explain what I mean. You can decide for yourself if, based on the integration process, are we kind of inherently calculating the work required to lay the first layer of stones as well. But, but like, as far as the work required to build the pyramids, I mean, it's a lot more than just literally lifting the stones. I mean, there's a lot of effort in all kinds of things. Just imagine pushing these stones horizontally, not just lifting the stones, but actually moving these horizontally. That must have taken an incredible amount of work. So it's a simple case here of the work required to, just related to lifting the stones against gravity, not considering that. So yeah, you have the first layer laid, and then now you got to come and get the stones off to the side, lift them up, and then move them all the way over. So, don't get bogged down with it. This is all about just illustrating integration. Okay. Even furthermore than that, apparently it's a really big mystery on how they cut these stones, like out of cliffs rock that was miles away, and then moved all of these enormous stones miles away to this location. That takes an enormous amount of work and effort. So, we're not even talking about that. But all right. So the idea is we've got this pyramid here, and which, something like that. And there's its height. So this is 756, and 481. And so for part A, all they're asking us to do is calculate the work done in relation strictly to lifting these stones up and putting them in place, lifting these stones against gravity and putting them in place. And I was thinking that we wouldn't be including the first stones, the first layer, because those, are at ground level. But, when we look at the integration process, I guess we're kind of integrating through the first stone. So I would say that, yeah, this integration process does include that first layer, strictly when it comes to like lifting that weight against gravity. I don't know. Comment on your opinion on that. If this integration is kind of inherently including the idea of lifting these stones up to put them in place, this first layer. So what we're going to do is, as the independent variable, we're going to use the height axis. So this is, we'll call this x. And this is x is equal to 0. That's x is equal to 0 at ground level. Okay? I mean, let's call it y. Why not? Up and down is y. Or z, actually. Z is, you have x, y, and z. Let's call this z. And the reason why we want to use this as the independent variable is because this variable is directly related to what we're trying to calculate, like the work done in lifting these blocks against gravity. And so at each position, z, we can think about there's a cross-sectional area of the pyramid, of which that cross-sectional area, if it cuts through the z-axis perpendicular, then the entire cross-sectional area is at the same height. And that's useful to us because that's kind of what the work done for that entire area, like lifting that area off the ground, you could think about, is there. It's all the same. So this is a good independent variable to use here for what we're trying to calculate. But we're not dealing with planes here. We need volumes because we're thinking about volume of limestone. We have the density of limestone. And so in that case, we're going to break down the independent variable axis into equal width pieces. And then for like each of those pieces, we're going to have an element that represents what we're trying to calculate. And so if we're trying to calculate the work done to lift limestone against gravity off the ground, then we're going to need a volume element, so that with that volume element, we can get the weight of limestone in that volume element, and then times like a height value off the ground. So we'll have the weight times the height. That's the work done to lift that weight off the ground. Okay, so at some height z, you can imagine we've got this cross-sectional area of the pyramid at any given height z. But then we'll think about, though, that so we're breaking up the z-axis from 0 to 481. We're breaking that up into equal width pieces, delta z's. Each of those delta z's is going to be the thickness of a rectangular prism, and with the bases of the rectangular prism being a cross section of the pyramid, like this. Now, which cross section is the one evaluated at the lower or upper endpoint of the delta z? Well, with integration, it doesn't matter. But if you were doing an approximation, we would think about it as the midpoint. So yeah, I guess if we're doing it, if we're going to choose like n is equal to 10 of these rectangles, then we would do it at the middle of we'd evaluate the cross-sectional area at the middle of the interval, right? So we've got these elements here, these rectangular prisms that represent, it's a certain amount of limestone, a certain volume of limestone, okay? But we're not trying to calculate the total weight of the pyramid. We're trying to calculate the work done to build it. And so the idea is each one of these rectangular prisms is lifted z above the ground. So you take that weight times the z, and that's the work done. And if we go from z is equal to 0 to 481, we can like sum all of these pieces, right? You get the volume of limestone in each rectangular prism, and you sum all of those up, the work done in each of those pieces, and you get the total work done to lift all these stones against gravity to build the pyramid. Okay, so the work done in lifting the ith rectangular prism, so ith being, you separate this into, it's the delta z is b minus a, so it's 481 divided by the n that you choose, the number of pieces that you choose. And so if we chose 50 pieces, 50 of these rectangular prisms, then w of like the 10th piece is what? Well, actually first we're going to need to get a function to get the side length of the square, because this is actually it's going to be a square, not a rectangle, because the pyramid is a square. So each cross section is a square. So we're going to need to get the side length of the square cross section as a function of z. How do we do that? Well, it's linear, right? The square side length decreases linearly all the way to 0 at the top. So the we'll call this just, this is x, x. So x as a function of z is what? Well, we start at 756, and then this decreases all the way down to 0. So we're going to have 756 here divided by what? Well, divided by 481, the height of z. Why does this work? Because when z is 481, this is 756, it goes to 0. When z is 0, this is 756. So it just decreases linearly all the way from 756 to 0. All right, 756 divided by 41. $1.57. So there we go. Okay. So now with that, the work done in lifting the ith block is what? Let me move this. Okay, so the work done lifting the ith block is the cross-sectional area of a rectangle of a square evaluated at z, but you know, which z position, which z do you evaluate? Do you get the cross-sectional area of the square? At the bottom endpoint or the top endpoint? Well, it does, we're just going to put zi star. But you would do the midpoint if you were actually doing an approximation. But so, all right, we need to first get the weight of the limestone in this square prism here. So the volume is this squared. So that's the cross-sectional area. So 756 minus 1.57 zi star, this squared, times delta z. Okay, now times, that's the volume of the square prism. Now, so what's the weight then? Times 150. Right? But then that's the weight of that the limestone in that square prism. But now what's that times the height that it was lifted? We have to put times z. We'll put zi star. And that's the wi. Okay, so this is 150 zi star okay, and so approximately this work done is, what you do is the sum from I is equal to 1 to n of this. 756 minus. So if you want to approximate the total work done to lift all the stones to build a pyramid, you could choose. So again, you choose any point you want to evaluate the square within the interval, and you choose like n is equal to 20, n is equal to 30, whatever. And so, but what you can see here is, well, it's not that easy to see, but if you made n too small, then the intervals would be large, and error would come in because, depending on the z position you chose to evaluate the square cross-sectional area, in the square prism, there would be too much or too little limestone weight. And you can imagine, just calculating the volume of the pyramid, regardless of, when we go back to calculating volumes, if you approximated it with too small number of right cylinders, you can think about the approximation with like 5 of these right cylinders here, it wouldn't be that good, right? You'd have it would be either too much volume or too little volume, and so that's how you can see the weight would be off. That's why the weight would be off. And then furthermore, if the delta z's were too big, then you would, as far as calculating the distance that weight was pulled up against gravity, what would you use for the distance? Like you would pick the midpoint of the interval, and that would be like, you would use that midpoint. You would be assuming that all of the limestone within the square prism was moved up that same distance, which would be based on the midpoint. of the interval. But if the delta Z is so big, then you have like a large difference in heights of limestone that you're all assuming are being lifted one height. So that's where the error comes in. It comes in with the weight of limestone within each square prism, as well as the height distance that you're saying that you're lifting that limestone up against gravity. But as the number of pieces gets really large, so as the delta Z goes to infinity, those errors get eliminated as n goes to infinity, because the height distance that you're lifting each square prism against gravity, they all converge, right? That's the whole idea, that the Zi star, as n goes to infinity, this doesn't, the Zi star, the position you pick doesn't matter. They all converge to the same value. The upper, the lower, they all converge. So as n goes to infinity, the height value is just going to be Z. When we make this an integral, the Zi star just becomes Z. Now, when it comes to the weight of limestone, that all goes away. Because when you think about it from the perspective of calculating volumes, and so if we were going to calculate the volume of a pyramid, we would use that right cylinder, the initial right cylinder method. That's the only method to use unless it's a solid revolution. You can choose between two different methods. But so using that right cylinder method, we've got these right cylinders here, and we've proven that as n goes to infinity, you're hugging the shape of the actual pyramid, of the actual master shape. Well, that just shows you that. So that's what that means then. So if we're getting the exact volume right, then the actual approximating square prisms are approaching the actual weight of limestone. Because think about it, if we have a formula that we can calculate the exact volume of the pyramid, and we know the density, I mean, at least, again, it's simplified. It looks like there's holes in here. It's not the exact volume, but if we can calculate the exact volume of a pyramid like this, we have a formula. If we have an integration technique that allows us to do that, then we can calculate the exact weight. So as n goes to infinity, the weight of limestone within each square prism is approaching the actual weight. The error goes to 0. Okay, so let's do that. Let's take the limit as n goes to infinity of this. That's equal to the work done, since we're taking the limit as n goes to infinity. So it goes 1 to n. Okay, now let's put this in integral notation. This limit as n goes to infinity of the sum, that's the elongated s. We're going from 0 to 481. Okay, now the Zi star as n goes to infinity, it doesn't mean anything anymore. So that's why we just put just the variable. All right, delta Z as n goes to infinity, that gets infinitesimally small. So this is dz. And there we go. Okay, so now let's just use our calculator to get this definite integral. So we've got 150 times z times 756 minus 1.57 times z. Store that as the equation E. So now we want to take the definite integral from 0 to 481 of the equation E with respect to z. Oh, wait, no, this is squared. So this should be squared, squared, squared. Okay, so let's try this again. So the equation is 150 times z times 756 minus 1.57 times z. That's squared. Okay, store this as the equation. All right, now we want to do the definite integral from z to 481 of the equation with respect to z. 1.66 times 10 to the 12. That's going to be in foot-pounds. So that's the work required to lift, just in terms of lifting all these stones up against gravity and putting them into position in the pyramid. Okay, part B. If each laborer worked 10 hours a day for 20 years, for 340 days a year, and did 200 foot-pounds per hour of work in lifting the limestone blocks into place, about how many laborers were needed to construct the pyramid? All right, this is like a unit conversions problem here. So, okay, it took 1.66 times 10 to the 12th foot-pounds of work to lift these stones to build the pyramid. But it tells us that each laborer did 200 foot-pounds per hour of work. So we can do it, let's say 200 foot-pounds per hour per laborer. Okay, so these cancel. But now our units are hour laborers. We're looking for just laborers, number of laborers. So how do we cancel out this hours? Well, we just need to find out how many hours did it take to build the pyramid. Well, it took 20 years, but that doesn't mean they were working 24 hours a day for 20 years. It was 10 hours a day, and they weren't working every single day. It was 340 days a year. So 340 days times 20 years, and then 10 hours a day. 68,000 hours. Now we're in laborers, number of laborers. So about 122,000 laborers.